All right, so in part 2 of the graph, we're going to talk about two different ways where we can traverse a graph. Just like before, when we introduced the binary tree, the traversal method in the context of the graph are designed to just visit vertices one after the other, following specific rules that was pre-specified. So in this lecture, we have two strategies we're going to introduce. The first strategy focuses on the depths. One intuitive way to understand is that understand this particular method, we call it DFS, is that we're going to follow along a particular path. Whenever we can, we try to extend this particular path until we have nowhere to go within this particular path. Then we'll begin backtrack and look for some other alternative. For the second strategy, which focus on the breadth, what we try to do is that for all the vertices that's out there, we focus on the vertex that can be reached within same numbers of edges, starting from, for example, one edge that's reachable from the current vertex. We move on to all the vertices that can be reached within two edges, so on and so forth. So we'll first start with the recursive version of the DFS. This particular method, as before, is very intuitively designed. The input variable of this particular method is the vertex that you would like to start your DFS traversal. First thing you do upon entry to the function is to visit this particular vertex. The visit of this particular vertex simply means that you set the label of visited to become true, to indicate that this particular vertex has been visited already. After that, what we do is that we look at all the vertices as inside the agency list, and we visit them one by one. So, of course, one very important thing in the traversal is that for a particular vertex, we will never visit it for the second time. So for the neighbor that's coming off the agency list, right? This is ICE vertex within the agency list. We're going to check whether or not this particular neighbor has been visited. Right? So this is the purpose of this particular function that we have introduced in part 1. If this particular neighbor has not been visited yet, we will start another recursive call over here. Okay, so if we follow that, right, so this is the agency list that's corresponding to the graph on the right hand side over here. Okay, and our beginning node is actually node A. This is the starting node, right? So we look at A over here. Remember, we look at all the vertices in the agency list, right? So we have B and C. So we look at B over here, right? This is the very first vertex in the agency list. We will visit that node immediately, right? Because of the recursive call. So the number on the right hand side indicates the sequence of the traversal, right? A is the beginning vertex, so this is the first visit. B is the second vertex that's been visited, so this is the sequence number 2. And then we will visit the third one, right? Because once you enter B, you look at B, right? You look at all the options, C, D, and E. You visit the very first one. Again, over here, we'll make sure that the nodes is only visited for one time. So for the visited node, you can cross it out. A has been visited. B has been visited as well as the second one. And from B, you can go to C, right? So it means that C has been visited as well. And from C over here, you can go to A or you can go to D, right? But remember, you never visit a vertex for the second time. So A over here, this is out of consideration. You cannot go visit that anymore. You can only visit D over here. So D has been visited as the fourth vertex. And from D over here, you can go B or F. Again, B has been visited, so you cannot visit that as well. So you can only visit F, right? So that will be the final node that you can visit along this particular path. But again, this is not comprehensive yet, because from the F, you'll backtrack to D to look for some other alternative, right? But from D, you can see that you have exhausted all your options. B and F are both visited already, so you cannot do anything. So you backtrack again to the case of C. Again, over here, from C's perspective, all the nodes has been visited. So you backtrack to B. From B, you can see that C has been visited, D has been visited, but E has not been visited yet, right? So E will be the next one that you visit. You branch it out from the vertex B to indicate that you visit this after you finish this particular branch of the path, right? So you all the way, you backtrack to B and look for some other alternative. In this case, it will be E, right? So this is the sixth node that you can visit, and this is basically it, right? So you backtrack to B, again, look at it. You don't have any option anymore. You backtrack to A, again, look at A, B has been visited, C has been visited, so nowhere to go. So you terminate the process. So if you write down the sequence of the visit, it will be A, B, C, D, F, and then E, right? So this is the sequence of the visit. So this is suppose you trace the traversal by using recursion. You can also trace the execution of DFS by using stack, because remember from week 6, sorry, when we introduced the stack data structure for the very first time. Stack is the type of a linear data structure that have this special property of last in and first out, and because of that, we illustrate that you can use the stack to emulate the execution of recursion. So over here, we're going to do very similar things. Okay, so we always will return the newest item that's been added to the stack. Okay, so this is a slightly longer version. If you look at it, very similar, except that we apply the principle that we have learned in week 6 to replace recursion with the use of a stack over here. Okay, so we are not going into the detail. You can look at this particular code over here and compare to the recursive version to see how they are related. So we use the real example to illustrate how you can trace the execution of the DFS by using stack data structure. So the very first node that we're going to start our DFS is the same as before, is the vertex A, right? So the first thing you do is that you push that into the stack. Again, this is a stack, so you actually have direction. You have to very clearly denote where is your button, where is your top. The top in this case will be on the right hand side. So the next step is that you're going to pop the node A out. At the moment that you pop the node out, you will perform the visit. Right? The visit actually happens when the node is being popped up, not at the time when the node is being pushing. So you visit A over here, you look at A, your agency list contains B and C. You're going to push all of those nodes that has not been visited into the stack. Right? So again over here, you can see that we push in C first, followed by B. Right? Because we like to maintain the alphabetical order. Right? So as a result, what we do is that we're going to do the pushing from the final element in the stack all the way until the final element in the agency list to the first element in the agency list. Right? So C and B are being pushed in, right? Last in, first out. So the next element that you process will be B. Right? So again, at the moment that B is being popped off, you also visit B. Right? So again, you look at B, you can visit C, D, and E. Right? So you do the pushing from the tail. It's going to be E followed by D followed by C over here. Right? So E, D, C. So you push all this element in according to the order being written down over here. So you see that in the stack, there's actually 2 occurrences of C's, which is okay, right? Because if you look at the code, we can go back to the code later after we finish this particular exercise. But you can see that before we visit a particular node, we're going to check whether or not the node has been visited already. If the node has been visited, then we will not do the second visit. Okay, so this is step number 2. Step 3, again, we pop out C, right? And then we visit the C because C has not been visited yet. And C actually have 2 nodes in the agency list, is A and D, but A has been visited earlier, right? So A, we will not push it into the stack. We only push it into the stack as D over here, right? So again, over here, you see that there's 2 copies of D. So D being pop out, right? And from D over here, you can see that you should push in B and F, but B has been visited earlier. So you're not going to push that in, you only push in F, right? So this is now the content of the stack. Next step, you pop out F, and at the same time, you visit F also, right? So from F, you have nothing. This is the end of the path, so you cannot push in anything. So now, right, so you see the first example where we pop out a node from the stack, but because D has been visited earlier over here, we will not be visited that particular node for the second time. And again, all the nodes B and F has been visited previously, so we are not going to push the list, the nodes in the agency list as well. Okay, and E over here, you can see that this is the next in line, right? So this is the final node that has not been visited yet. So we pop it out and we visit that particular node. In the final, we still have something in the stack, so we pop it out, and this is basically it, right? Because C has been visited, so we will not be visiting this particular node. So if you try to collect the sequence of the visit, it's going to be the second column over here. Is going to be A, B, C, D, F, E. You can compare that against the sequence that you obtain using the recursive function. They should be exactly the same if you follow the rule correctly. Okay, so this is the second potential implementation of DFS, but this time we do it by using the stack. Okay, so the breadth first search follows very similar principles. Only difference over here is that the list of the candidate nodes that we should visit now are being stored inside the queue, right? And we trace the execution of the nodes by sending in the candidate node by using the in-queue operation. And then when we want to obtain the next candidate node, we use the dequeue operation. Okay, so let's see how it works. So this is the code that we have, breadth first search. You can see that instead of having a stack, we have the queue over here. All right, we create an empty queue, and then we in-queue the first vertex. We always execute when there's still something inside the queue, right? One thing to keep note is that the visit and the in-queue operation now happen in the same step, right? So you can see that for all the neighbors that we get out of the current vertices agency list, we try to check whether or not that particular node has been visited. If not visited yet, we're going to visit that node, and at the same time, we in-queue that node into the queue, right? So this is something different. If you look at the case of DFS, when we pop the node out, that's the time we're going to visit the node. When we push the node in, we don't perform the visit yet. Okay, so let's see how it goes. Right, so again, the first node is being in-queued. Right, so as you can see over here, right, visit and in-queue. This is 2 actions in one go. Okay, right, so again, here we also denote very clearly the direction of the queue. Over here, the head of the queue is to the left-hand side. There's only one element in the queue, so we dequeue that. And then you can see that from A, we have B and C. Here, we just in-queue the candidate nodes by following the order that we have in the agency list, which is following the alphabetical order. Right, which means that all things being equal, if you have multiple choices, you'll pick the next node by following alphabetical order. Okay, so you can see that we have B over here, we have C over here. Next node we get will be B, right? So from B, you can see that again, it would be helpful if we actually label the nodes has been visited. In this case, A has been visited the first, and then B and C has been visited the second. You see that they are all the nodes that you can reach within 1H from A, right? And then from B, you can see that you can go to C, D, and E, but C, you will not visit that for the second time. So that's why you only have D and E, right? So again, at the moment that you include them into the queue data structure, you already visit them, right? So you cross them out. Okay, so again, C, D, E, you have C. You don't have anything to do, right? So you basically just from C, you have A and D, but both A and D has been visited previously, so you do nothing. So you have D and E. From D, actually, you can see that there's one more element, F, that you have not seen before. So you're going to include that node over here. And of course, you visit that. So that's the final two candidates that you have. You try to expand E, but nothing to expand because D has been visited already. And finally, it is F, right? And by which time you reach F, the queue becomes empty, right? So this is the termination. So if you want to put down the visit sequence, this is where the sequence can be extracted. So if you put it down, it will be A, B, C, D, E, F. All right, so this is the sequence of the visit.